Hello everyone and welcome. I am Dr. Guido Marwa, Assistant Professor of Chemistry at Mohammed Khayder University of Biskra. In this video, I am pleased to introduce the first chapter of the thermodynamics course designed for first-year students in the Common Core Department of the Faculty of Science and Technology. This chapter is entitled Generalities of Thermodynamics. The content of the chapter covers several key topics, including specific objectives and thermodynamic systems, and the type of thermodynamic systems and thermodynamic equilibrium and its types, and zero law of thermodynamics. Regarding the specific objectives of this chapter, by the end of it, students will be able to define thermodynamic systems, state function, and state variables, explain the concept of thermodynamic equilibrium, and distinguish between thermal, mechanical, and chemical equilibrium, and classify different types of thermodynamic systems and processes, analyze energy transfer mechanisms between the system and environments, including phase change and cyclic processes. So, what exactly is thermodynamic system? This image helps clarify the concepts. A thermodynamic system is a defined portion of the universe selected for study. It is separated from the surrounding by real or imaginary boundaries, through which energy and matter may be exchanged. The surrounding includes everything outside the system that can interact with it. Together, the system and its surroundings make up the universe. A system can exist in different physical states, solid, liquid, and gas, depending on the situation. Thermodynamic systems can classify it into two main types: real systems, which are physical systems that exist and are used in experiments. For example, include the liquid in thermometer and the gas inside the cylinder, or even the Earth and its atmosphere. Well, in ideal systems, which are simplified theoretical model used for calculation, such as an ideal gas that assumes no intermolecular forces. Thermodynamic systems are classified based on how they interact with their surroundings. The three main types are open system. This type allows both energy and matter to be exchanged with its surroundings. This means that heat, mass, and other forms of energy can flow in and out of the system. In closed system, energy can be transferred but no matter is exchanged with the surrounding. The system mass remains constant. Isolated system. This system does not allow any exchange of energy or matter with its surroundings. In reality, perfectly isolated systems don't exist, but some systems can approximate isolation over short time periods. A system is in thermodynamic equilibrium when its macroscopic properties such as pressure, temperature, and composition remain constant over time as long as it is isolated from its surroundings. This means there are no unbalanced forces or energy flows within the system. Consider a closed container of gas. If different parts of the container have different temperatures, heat will flow from the hotter regions to the colder ones over time. When the temperature becomes uniform throughout the system, it reaches thermal equilibrium, which is a key aspect of thermodynamic equilibrium. To be in complete thermodynamic equilibrium, a system must satisfy three conditions. Thermal equilibrium. This occurs when there is no temperature gradients, meaning heat does not flow between parts of the system. For example, a cup of hot coffee left in a room will lose heat to the surrounding until it reaches the same temperature as the room, achieving thermal equilibrium. Another one, mechanical equilibrium. In this state, no unbalanced forces act on the system, meaning pressure remains uniform throughout, such as a gas trapped inside a cylinder with a movable piston is in mechanical equilibrium if the pressure inside the cylinder matches the external pressure exerted on the piston. Chemical equilibrium. At this point, no net chemical reactions are occurring, where the concentration of the substances remain constant. For example, in a closed reaction vessel, the reversible reaction of hydrogen reacts with iodine, reach chemical equilibrium when the rates of the forward and reverse reaction become equal. The zeroth law of thermodynamics states that if two bodies or systems are in thermal equilibrium with a third body, then they are in thermal equilibrium with each other. For example, consider here in this image three systems A, B, and C. If A and B are each in thermal equilibrium with C, the zeroth law asserts that A and B are also in thermal equilibrium with each other. This principle allows for the practical definition and measurements of temperature. When a thermometer is in thermal equilibrium with a system, the reading on the thermometer represents the system's temperature. The zeroth law is essential in thermodynamics, supporting both theoretical understanding and practical application in temperature measurements. This brings us to the end of this video. Thank you for your attention, and I look forward to seeing you in the next video.